Good afternoon, everybody. I'm just going to introduce myself. My name's Bill Ritchie. I suppose qualification for doing this is I started life as a coastal geomorphologist, and my last paid position was as director of the Aberdeen Institute for Coastal Science and Management. I'm also quite involved with with MASTS. The purpose of this particular talk today is given in the title, Relative Sea Level Change Scenarios for Regional Scottish Coastline. But the wider background, and I suppose the raison d'etre, was the observation that in relation to climatic change, there is, use my words carefully here, almost an obsession about sea level rise. And I'm going to put this in context of the other factors that, in my view, are probably more important in managing the Scottish coastline and exploiting it in the nicest possible way into the future. And just last week, I read a survey in a major newspaper which said they'd asked people questions about did they believe in climatic change, and almost everybody said yes, without defining what they meant by it. And then they said, well, what do you think is the most important factor or problem? And 65% said rises in sea level. This was a public survey. So that's perhaps a justification for moving on to this. Why so much emphasis on sea level changes? My opinion, it's very, very, very difficult to model the complexity of all the causal factors. There are fantastic models running in huge computers all around the world, and it's very, very difficult to do. The other problem is the data set is, good data, is relatively short in statistical terms. However, moving from cause to effects, I think most people find it easier to understand the effect of something, even though they don't understand the process and the complexity. So I think there's complexity in the causality, but there's perhaps something fairly obvious about the effect, and in particular, what happens at the coast under various scenarios. The term we should use is relative sea level change. Not absolute, relative. It's relative to the land, it's relative to different parts of the coast, it's relative to parts of the world. But one factor, it's but one factor. So when I was teaching basic coastal geomorphology many, many years ago, I always started with this particular slide just to let the students know where I was coming from. And this was really any coast. If you look at any coast in the world, what are the 7 boxes you've got to consider? Rock type, relative changes in sea level and on different scales, from tides to waves through geological change, availability of materials, and I'll say right now, in my mind, that is the most important factor of all. And that's sand and mud and sediment cobbles. How much is it? Where is it? What's it doing? Marine process is obviously critical. And in this case, unlike popular understanding, the main process is not the tide. I used to teach evening classes and I used to ask the people, what's the most important factor in coastal change? Tides. It's not, it's waves. Overwhelmingly waves. Land processes are sometimes forgotten because remember, the coast is where the land meets the sea. And we ignore land processes, particularly fluvial processes and water movements from the land at our peril. Ecology, probably the least studied factor in coastal geomorphology. The effect of biological factors on the coastal zone. As a coastal geomorphologist, I'm saying that, not as a biologist. And of course, around the world, increasingly, we don't have all that many natural coastlines left, whatever you mean by natural. So we've got to think of land use and man-made changes. They're all interrelated. It's a natural system. all 7, and sea level changes are not necessarily the most important, depending perhaps on the time scale that we're discussing. So let's just run through them. Coastline of Scotland, one of the most varied in Europe, indeed in the world. First factor, the basic geology, the structure, what's there. What did we inherit from millions and millions of years ago? Incredibly complex, and therefore we have this fantastic scenery. But the most important point is, in terms of sea level change, in that most of the coastline of Scotland is made of hard rock, it's steep, and therefore any change in the level of the sea, particularly over a historical time span, has little or no effect on most of the Scottish coastline. Now let me begin, or move on backwards as it were. There's nothing new in all this, because in this superb publication, which I'm sure you've got, the National Atlas of Scotland, it was produced in 2011, what it says at the beginning, trends in sea level vary greatly in different sites. Much of this variation is probably caused by differential movements on the land in which the tide gauges sit, and it's moved by the land continuing to move after the Ice Age. The rate of sea level rise around the United Kingdom coast, adjusted for land movements, was about 1.4 millimetres per year throughout the 20th century. And that's the official government publication. Now, point right at the beginning is I'm not going to say much about most of the Scottish coastline because it's like that. However, if we contrast a very old photograph, quite deliberate, 1973, Aberdeen, mouth of the Don, we have the other type of coastline where it's dynamic, it's mobile, it's low, it's soft, it changes every day, and it also shows the interplay, and I'll mention this later, fluvial forces coming down down the River Don, and the various movements caused by the waves with a tidal component along the Aberdeen coast. And it does show, if you just, if I get the right bit of the pointer here, it does show the man-made structures that are trying to arrest and change the natural coastal processes. Now, factors on my original diagram were waves. Now, I'm not going to talk for hours about different types of waves, but here at Buckhead you can see how a coastal geomorphologist would look at it. We use an artificial structure because that tends to clarify things. What we have is the deep water coming in. It's beginning to feel the bottom at approximately half the wavelength. It begins to distort. It begins to modify. It changes its orbital characteristics to more a backward and forward movement. You go around the tip of a structure. It begins to diffract. You can see the waves turning. And as it gets into shallower and shallower water, this curvature increases, and that's called refraction. So you've got reflection coming off the seawall. So every time you look at waves, 4 things: reflection, diffraction, refraction, and how it finally breaks in the intertidal area. That's what actually counts. Shallow water, normally after the breaker zone, and then movement of the sediment. Now let me declare an interest here. This is not a presentation about causes and predictions of climate change per se. It's not my subject. I'm not an expert. I just read the various papers, and I've been reading them since, as you'll see later, since the 1960s. And just as a little side note, I'm definitely in favour of climatic change. My first academic paper was the measurement of the retreat of a glacier in Norway. And so I'm quite convinced about climatic change. What I'm not getting involved in is the rate, the predictions, and the effect of carbon dioxide and methane and all the other gases. That's not my subject. I'm just going to use it as a scenario. However, I must contextualize what I'm going to say by using historical evidence of relative changes in the land-sea boundary to get the modern concern with sea level changes of the public, of the planners, politicians, into some kind of perspective. Now, sea level changes have been with us for a very long time. This is the different stages. It's an extremely nice diagram, and it shows that over the course of time, this is the west coast of Jura, you can see that since the Ice Age, late glacial, post-glacial, Holocene, 10,000, 15, 20, 100,000 years ago, the sea level on the west coast of Jura has fallen. And you have beaches up there, you have shingle terraces, you have 3 or 4 different sequences of cliffs. And that's quite good, not difficult. Higher sea levels relative, for it could be the sea being higher, or it could be the land being lower. So you've got to, that's what we mean by relative. So moving on, the other extreme, which is much more difficult because it's not nearly so common, is what evidence do we have of lower sea levels? And the reason is, it's not a joke, it's all under the water, or it's on an intertidal beach. So this, in fact, this is from Pabay in Outer Hebrides and Bimbecula in the Outer Hebrides. This one was taken by sub-aqua divers. It's organic material, it's a peaty-like material, it's organic, and the bottom layer was dated to about 7,000 years ago. So, and it was about 3 meters below present mean sea level. Now, there are complications in interpreting submerged organic deposits. But the next one, whoops, back up. The next one in Bimbecula is actually got a bit more to it. It's at the low point on the beach, but you notice the compression. It's mainly made up of fresh water, peats, and all the proper vegetal remains and pollen and so on. But what you can see is compressed because the land, the macher, has moved over the top of it, and you can see all through it different layers of sand. And this has been used by many of us and archaeologists to say, when did the first sand start blowing? When did the macher form? When did the dunes build up? And so that's the stratigraphy, as well as the chronology, particularly in the pollen and the carbon-14, are essential to this story. Timescales. You can never consider any topic like this without reference to a timescale. Basically, with regard to Scotland and probably about half or 2/3 of the planet, you have to think in terms of, geologically, the Ice Age, the big event. And what we have to say, or I would say, is in a way we're still in the Ice Age. We still have ice sheets. We still have ice caps. We still have glaciers. So a reasonable definition is that we're still really in the Ice Age. However, as the Ice Age went through its different phases, there was at least 4 advances and retreats, build-ups and sinking downs. But what we're dealing with now is perhaps the second one down, ice melting. Now, ice melting, historical is probably not the right term, it's still geological. Say back over 25,000 years or so, there's no doubt the ice melted, it didn't melt all at one time, it went back and forward and so on. So what that did was introduce changes in the volume of the water in the oceans and seas of the world, the totality of water that was locked up in ice, but at times, and right now, it's all melting and water's being added. Now there's a slight complication here that it's not, the water doesn't stay the same, because if you're in a warming period, in my day we used to call it the amelioration period, then the temperature of the seawater increases, it expands, and there's a greater volume. So it's not, even that's not straightforward. So recent though, we talk about ice melting, and right there, anthropic is the discussion that the rate of this melting is in some way being accelerated by effects of human activity on the atmosphere, probably, realistically, from maybe late 18th into the 19th century, a relative short time span. Now, this is a very old one, but it's one which I used to use back in the 1990s, and that was the predictions that were made by about 8 different agencies with huge computers trying to use what data there was from atmospheric physics, from climatical records, from meteorology, and somehow extrapolate that into the future. And not surprisingly, they come out with low scenarios and middle scenarios and high scenarios. And this is running through to 2100. And there's a kind of feeling, in fact, what data there was, and I think this is probably absolutely correct, that there is an acceleration and the curves are all moving upwards to the right-hand side of the graph. Now, there are much, much, much more recent graphs than that, but I don't want to get bogged down in the detail. It's just this general movement. But the important thing, in my view anyway, is to look at the variation. Sorry, I keep hitting the wrong button here. The variation between what is a high scenario and what is a low scenario. And to this day, there are still high, medium, and low scenarios. However, it's not my subject. This is just to contextualize it. However, what we have to consider when we're looking at the Scottish coastline is, well, really, what this is all about, well, it really is dominated by glaciation and deglaciation. Ignore the one on the left. That's really the movement of the ice masses over the Scottish ice cap, linked up with Scandinavia in a much earlier period, which is in fact called the Anglian. But the important one is the right-hand one, the Ventian. That's about 11,000, 12,000 years ago, roughly. And what we had was separation from Scandinavia and the ice sheet of Britain moving in those directions away from a centre point, which was roughly around about Kinlochleven, not Kinlochleven, sorry, I forgot the name of it. Anyway, in there, it's roughly about the middle, and it moved laterally out of that, and the one we're having to look at is the directions as it moves out. Orkney probably went that way, Shetland went that way. So we have this ice sheet, it's melting, it's breaking up, and the periphery of the ice sheet is, I'm terribly sorry about that. The periphery of the ice sheet is critical to what I'm really going to say actually quite soon. So, ice sheet, very, very thick, big dome of ice, very heavy, locking up water and moving out and melting. And in the sense that it's melting, what we should begin, sorry I keep doing this, what we should get is that margin, you really get the right pointer here, that margin there is going to retreat. It's all going to shrink back in to the central massif of the Scottish Highlands. So imagine that line coming back in. I'd ask you to hold that in your mind. Now, sea level rise, better terminology, relative, I've said that. Accelerated, because it looks as though all the predictions are accelerating, that's fine. Sea level changes are strongly regional. I'll come back to that in a moment. There's nothing uniform about sea level changes around actual coastlines, particularly those that have been glaciated. So the actual change in the sea level, the land-sea boundary, is a combination of eustatic. Now, it's the first time I've used that word. Eustatic is global. That is the amount of sea level rise that we are getting, have got, will get as the ice melts. And that means there'll be a rise in the Pacific, the Antarctic, North Sea. That's the baseline of a rise in sea level. However, that amount, which is almost absolute, the eustatic, is affected, modified by isostatic. That's to do with weight, going up and down on the Earth's crust for different reasons. But for the moment, we'll deal with ice, so it's called glacio-eustatic. But there's another factor, which is tectonic. Almost nobody would study sea level changes around the Mediterranean because of volcanism and earth movements and islands going up and down and coasts going up and down. You can't work it out because that's a tectonic movement. The other area where I've done a lot of work personally was in the Gulf of Mexico, and there's an isostatic sinking because of the sheer weight of the Mississippi Delta. It's actually pushing down the cross, and one of the highest rates of sea level change in the world, rising relatively, is the Gulf of Mexico because of the weight of the Mississippi Delta. So relative sea levels always combine the global and the regional glacio-isostatic, tectonic, sediment loading. Now, one of the classic diagrams, which was originally produced way back in the 1970s, was if we can't work out the rise in sea level because of all these complications of ice and tectonics and so on, is there anywhere we can look? So they actually looked to the intertropical locations in the Pacific mainly and the Atlantic. And the main data was coral reefs because they're very sensitive to the photic zone as it develops in particular intertropical, in fact, anywhere. So different parts of the world, they actually compiled all this brilliant work way back, done probably in the 1970s and then modified year after year after year. And what it does show is one of the great global knowns, that is about 25,000 years ago, most of the coastlines of the world were 150 meters below the present sea level. Therefore, almost every continental shelf in the world was dry land. Now, 25,000 years ago is coming out of the Ice Age. We're into the, and as we move forward in time, then that there is the volume of ice. You can translate it to water if you want. And there is the ice volume in relation to the sea level. So you've got the ice volume, water volume, and what you end up with is a rising sea level, relatively steady up through time till you get to about 5. Now, why did it stop at 5,000? Well, around about 6,000, it increasingly became evident in many parts of the world that things started to get complicated. That this massive rise out of the Ice Age was being affected by much more local factors. It was, in a sense, slowing down as we approached present sea level. Now, one of the classic ways of looking at this is to say, well, just that's the Pacific. Let's look at Scotland. So what we had 20,000 years ago, if you go to this bit here, the blue line, then sea level, remember the raised beaches and cliffs I showed you in Jura, sea level was falling. We had raised beaches, higher coasts, and then it started to turn. So as we moved roughly towards the present. However, this is the rub, if you go to the Outer Hebrides, the periphery, remember where the margin of the ice sheet was. The periphery, Shetland, Orkney, the Outer Hebrides, what you do, you start off down here the same way, but there the trend is exactly the opposite. And that is because it is, in a relative sense, submerging. So broadly accepted rates of change, 30,000 to 50,000, sea levels drop, 120 meters, 150. 15, sea levels rise to about 10 to 5 meters. The slide I showed you of Pabay in the Outer Hebrides and Becula were in that 6,000 year line, and they were about anything from 2 to 8 meters below sea level. And from 6,500, it varies around the present level and range. And it's mainly driven by the growth and decay of the ice sheets and glaciers. That's what it's all about. Now, so the evidence, we've done that before, regional variations, interface. Now, how do we illustrate this? Now, what we look at is we try and construct, or people have constructed isobases that relate. Now, that's roughly the same pattern as the ice sheet, centered over here and getting there and there and there. What it's saying is that at this particular time, 11,000 years ago, We look for the zero line, and there it is. So that's roughly the coastal elevation, that line. As we move out, what we find that around 11,000 years ago, it looks as though west and touching North Uist and Harris, it was minus 20. So we have different bits. I'm sure that's not exactly correct, but sort of concentric round about where the maximum thickness of the ice was. And therefore, sea levels decline peripherally away from that. So that's just a particular example picked out about 11,000 years ago. Now, we can just generalize a little bit further. Everybody probably knows this, but I'll just mention it to you. If we look at Scandinavia and you look at the green lines, because it still ice is statically rising, because the weight of ice has come off, you get areas that are getting higher. Relative sea level is falling. When you come down to the tip here of Skåne and the north tip, you're in about the zero line, and Scotland is similar to Scandinavia because it had an ice cap. But once you get down here, all the trouble really starts for poor old South England and South East England, because they're sinking anyway. There's no isostatic compensation in that blue zone. And this is just another variation done by different authors on the isobases, whether it was a post-glacial shoreline, or a late glacial, or dry ice, whatever. And there are hundreds of papers on this in the Scottish literature about where these coastlines and elevations of the sea were. So for Scotland, in general, submergence on periphery, minor submergence, no submergence for the remainder of the coastline. So Scotland, you cannot say one size fits all for the effect of sea level changes in Scotland. Simply impossible. It's highly regional. And bear in mind what I said at the very beginning, that most of the coastline, if it's rocky or a rock platform or a cliff, doesn't matter anyway if it's rising at millimeters in the decade. So if I go back to my original diagram, teaching, as it were, let's have a look at the other factors which I'm going to put it forward today are actually much more important for anyone concerned with the future of the Scottish coastline than sea level change, in a relative sense. So there we are, hard, high, slow to change, most of Scotland cliffs, low and soft and quick to change, estuaries and beach coastlines such as the Macar, and it's the type 2 coast that are of concern, because if we do have a significant increasing level of the sea, even though it's measured in millimeters and centimeters, then it is something that would have to be taken into account in any kind of planning or engineering or managerial solution. So here's a typical low soft coastline, but what we see here, this is in fact up at St Fergus in the North Sea, we're getting enormous changes in one tidal cycle. However, it's a very soft coast, very mobile coast, as is all the dunes and beaches of Scotland, and arguably we have to begin by saying, if we're going to look at areas where there might be problems, then the lower and the softer that coastline, the more concern we might have. And of course, the classic would be a salt marsh, where this is actually in Shetland, where even a small change of a few centimeters could totally alter the ecology, the sediment distribution, the way that salt marshes develop and grow and retreat. In the Outer Hebrides, here we have probably the area of greatest concern. It's out in the periphery, it's submerging, it's beyond the isobases, and it's very low and very, very soft for most from Barra right up to the tip of Lewis, there are relative few areas that aren't fairly low, soft, mobile. And of course, when you come to the estuaries, in fact, this slide was given at a MASTS lecture a long time ago at an ASM. My view then remains constant, no matter what we're talking about in terms of coastal management, then we have to consider that some of the most important parts of Scotland, the Tay estuary, the Forth estuary, the Solway Firth and the Firth of Clyde, they're not natural. This is a low water slide from Dumbarton Rock showing the dredged channel, like a canal that used to go all the way up to Glasgow. So it's a managed coastline anyway. It's heavily populated. And that introduces the final fact in the diagram is, fine, let's talk about natural coastlines and how they evolve, but we also have to consider that the majority of the population of Scotland actually live in the low coastlines, which in theory, and probably in practice, are more vulnerable to these changes that could occur in the future, and probably are occurring right now. So, short-term rises in relative sea level, not related to climatic change. Now, here's my argument, that there are changes being driven right now to the Scottish coastline that probably need some kind of attention and management. And the argument, these are probably more important since these elevations of sea level are an order of magnitude greater. They're measured in meters, because these are events that are occurring right now. They occurred 100 years ago, they occurred 200 years ago, and they're going to continue into the future. For example, a North Sea surge has a predictable return period about, certain measure every 50 years, 100 years. We have exceptional tidal levels. We have exceptional wave height and violence. So the question that arises from people who are concerned about climatic change tends also to look at, what about the frequency of these extreme events? There's a lot of research going on this. Some people say they're more frequent. In fact, that's the popular view. Some of the research I've seen say, no, they're not. We've had big storms with big surges in the past. 1953, for example, the biggest one ever. Now, here's the surge. And the good news for Scotland is that surges, which are, as you know, low pressure, north winds, high tides and all that, are a big problem. Absolutely. You wouldn't want to live around about there, where they get 4.5 meters of surge, whereas Aberdeen gets about 1 meter. And that's a big surge. And of course, the funneling effect makes it much, much bigger. So when you get down to London, you need a Thames barrage because it's predicted down there at 2.75 meters. The interesting area, however, is the Solway, because it's a macro-tidal region anyway. So if you have some kind of local surge, then you would have to take that into account. And an order of 1.5 meters, my eyesight isn't quite there, I think it's 1.5, additional to the normal tide would, of course, dwarf 10 millimeters, 20 millimeters in perhaps roughly the same time interval. And the same is true of significant wave height. This is quite an old one, but it hasn't changed very much. It's the one that's used for planning renewable energy and so on, where you can see the extremely high waves getting up there till, 7, 8 meters. That's a significant wave, which is the top 10% of all the waves. It's not all the waves, it's just a percentage of them. It's the measure we use, significant wave height. And I've seen it written that the significant wave height will get greater under certain climatic predictions, and the frequency of these high wave events will also get more frequent. I was at the talk in Orkney, I think Mark was there as well, and there was a paper given there, and I'm doing it from memory, and the suggestion was, doesn't look as though it's going to be more frequent and higher. But I haven't seen the paper, but that was, I think, what was said. Question, will these normal events be more frequent, more severe under climatic change scenarios? Question mark. You could put a double question mark on that. these normal events, such as surges, hurricanes along the west coast, big storm damage, will they be more frequent? Will they be more severe? Problem is, the data set is rather short. One of my colleagues who gave me much of this material, Professor Alison Dawson, worked in the Outer Hebrides, and he actually found that there was this terrible storm, which I'll show you later, when there was loss of life in the Outer Hebrides. But they looked as though there was an even bigger storm back at the end of the 19th century. So there's a data problem here in terms of good modelling. So here's one from Alistair Dawson, and of course, this has been an extreme event in the Outer Hebrides, the West Coast, the Atlantic. It was called a surge. It wasn't technically a surge. It was really a 110 knot wind coming from the west, high tide coinciding, and there was serious damage done to the infrastructure. And sadly, there was loss of life. There was a family which was drowned. However, the subtext of this really came from Mark's suggestion to me, and that was to say, okay, that's fine. MASTS meet with people, and these people are charged with management, they're charged with engineering, and they're charged with looking at what kind of research do we need, how should we apply that, do we have any sort of policy that would relate to the Scottish coastline. The first point is, of course we should, but there's always two policies, at least. One is do nothing, in that the forces are unstoppable, and the expense of doing something about it is horrific. Nobody would go down the line of do nothing. Society doesn't develop, doesn't react in that way. It used to be, and if I was using perhaps careful terminology here, but probably up until, I won't put a date on it, but much of the coastline of Scotland, maybe up to the 1920s, dating, it's kind of Victorian. And the argument was that you opposed, you protected, you built big granite seawalls, you built concrete cliffs, you put in structures that would prevent the damage from the sea and also prevent flooding, which is of course a different matter. The more recent trend, even in the most up-to-date coastal engineering textbooks, would say, I think we should think more about adaptation. Let's accept that there's going to be these storms, there are going to be high waves, and not try and fight them. Let's not oppose them. Wherever possible, let's try to adapt to this. So the official term is adaptation policy to changes to the Scottish coastline. If that is the logical conclusion, then there's limited resources. Therefore, and this goes right back to my very first point, if we've got limited resources, then the managerial resources should be focused, common sense, in areas of greater risk. Take the extreme, absurd point. There's no point in doing research and thinking hard, putting money into the cliffs in Orkney. On the other hand, if you're down in the Firth of Forth, near Grangemouth, very, very low, you've estuarine problems anyway down there, then you should think about, we've got to spend money here. Do we resist it, or do we try and adapt to what we know is going to happen? Now, on another occasion, I remember giving a talk some time ago to coastal engineers many years ago about the distinction between flood and erosion risks. They're sometimes confused, thought they'd be synonymous, but I think that's a topic for another time. Thank you. I don't know about the lights, but oh, I'm sorry, I know I have finished, but I just remember one thing, if you'll forgive me. Probably the best book I ever read on responding to changes in sea level was produced by the United States Academy of Sciences. And it was produced by a very distinguished panel of people in 1987. And you never see this quoted, but it's absolutely brilliant. I keep going back to it. And it actually said in its conclusions at the end, interesting one, by the way, this is in parentheses, studies of a very small number of tide gauges records dating more than 100 years. Here's something for Trivial Pursuits. The oldest being Amsterdam, which started in 1682. That was the first tide gauge in the world, apparently. Shows that after the removal of subsidence factors, where known, that's tectonic depression, sea level has been fluctuating through a range of not more than 40 to 150 centimetres in the last 300 years. And if you do the equations in this and take them forward, then they end up with a value which is somewhat similar, to put it mildly, to what was said in the Scottish report, where it says, if I get the right page, that it would be something of the order of about 10 millimetres, 1 to 10 millimetres. I've got to find the page. I put a little sticker in it, it's dropped off. But the point is, the prediction made in 1987 by the North American Academy of Sciences is pretty much what is happening today. So, what's the saying? There's nothing new, is there? But I really, when I actually thought that this report was so good that I actually went up from Baton Rouge to Washington to talk to one of the authors, because I was just so taken by it. And I didn't throw it out when I emptied my room in the university. So sorry about it. I should have raised that earlier. Okay, Mark, whoever. I don't know what happens now, questions or whatever. It's a bad sign. Yeah. You know, 5, the figures for 5 are, the East Coast is a bit more difficult because most of the research, actually for quite good reason, was on the west and north of Scotland, the Clyde. The most work on the East Coast was actually done by a school of geographers under a Professor Sissons in the University of Edinburgh, and he concentrated really in the Forth and the Tay. But the current prediction is that it will be just round about average for the British Isles. It's not exceptional one way or the other. And the value that, if I find this. Right, here it is. The rate of sea level rise around the United Kingdom coast, United Kingdom, adjusted for land movements, was about 1.4 millimetres per year during the 20th century. Now, what I can remember about the 5 coast, you'll be pretty much in about that. It won't be all that much higher, all that much lower. I think I did state that at the beginning, but it was worth mentioning and reminding me. But when you think about it, get on that beach, 1.4 millimetres. Compared with the possible shifts in sediment and the availability, in fact the non-availability of sediment feeding the coastlines of Scotland, then that's a much bigger programme. And one of the MASTS group, which are meeting at the annual science meeting, are actually going to concentrate on sediment deficiency. Where's it coming from? Now that the glacial legacy has been used up and translated. See, most of the coastline of Scotland inherited millions, if not billions, of tons of sediment, mainly sand and gravel, from deglaciation, from the meltwater, huge meltwater rivers coming out, continental shelf covered in sand. The area I've done most research is Outer Hebrides. If you go to the Outer Hebrides and you look at the continental shelf, there's not much sand anymore on the continental shelf. It's mainly rock. You look for the sand, it's already on the land. It's the macha, it's the dunes. So where's this new sand coming from? Very few rivers today flow into the Scottish coast carrying a lot of sediment. Most of it now is actually, I think, the ones I know of, because of land use changes and the lack of cutting through sediment, rivers are tending to bring down a higher proportion of mud, and because of land use changes, deforestation, irrigation, all that sort of thing. That's going into the estuaries. So that's why I said at the beginning when I showed the dawn, is coastlines are land and sea, and terribly difficult areas are deltas and estuaries, because of these huge fluvial masses of cold water or dense water or non-saline water, with or without loads and loads of sediment, what happens to it? And if we go back to the Aberdeen slide, you saw there was actually a subtidal delta coming out of the mouth of the Don. What happened to that sediment was it tends to move northwards. And you get changes along the coast which look as though they're deposition, or they look as though they're erosion, but in fact it's not. It's the reworking of the same material. It's just been shifted around, and the total volume of sediment is probably diminishing. And that's what one of the MASTS subgroup is going to concentrate in now that they've been set up. So in my 7 factors, I think I did say I would put my money on putting good research into sediment deficiency and movement, rather than agonizing over a few millimeters due to climatic change. Sorry, it's a long answer.
I know you've got strong views on it, but what does it say about our maps, given that we've got multiple maps and how far away from the trees?
No, the maps I'm most familiar with are done by SEPA, and they were based, I think they're primarily flood risk. SEPA, I think, did a very good job. They knew the variables, they knew the regional differences, and they were assiduous in collecting evidence, and they went, I can't remember which model they went for, but they had to go for some model, and they picked a model. And I thought they were pretty good. But what these maps tend to show are high risk scenarios for particular locations. And the public of late, probably since the 1950s, their main concern has been flooding, because you got all these dramatic photographs in newspapers of houses going into the sea and bridges disappearing, that sort of thing. And that's not just a marine thing, it's a fluvial thing. I think SEPA put both together, the fluvial regimes and the marine predictions. But it's like anything that you finally put down in a map, it's only as good as the time it was put down in terms of the data. And I think they're fit for purpose. Yeah, fit for purpose. Thank you very much for your attention.